All right. Thank you so much for the very kind invitation. As I said, I really appreciate it. And again, apologies for these technical issues that I hope will not come to bite me in later. Yeah, this talk is essentially like a presentation of this recent paper I wrote together with Benjamin, Alessia, and Mark. And it is about indeed examining the asymptotic safety scenario in quantum gravity from the point of view of the swampland program. Now, what does this mean? What this means concretely is sort of going at the foundations, right, of the whole program, or at least my particular way of understanding the program or thinking about it, and seeing if there's something that we can say without relying on any specific calculational framework or approximation scheme or anything of the sort. And this is essentially to try to compare, if you will, this approach with any other ideas about quantum gravity in a sort of a unified way. Now, it goes without saying that what will follow is but my personal perspective on the story. 1 out of 4 authors of this paper, after all, is all I am, and I am not unbiased by any means, right? Still, I will try to be, right? I will try to be as objective as possible. I will try to state, let's say, facts or things we can all agree on as much as possible. And other than that, I fully acknowledge that what I'm going to say, how I'm going to say it, can be subject to loopholes. Everything can be questioned. You may have questions that I cannot anticipate here. So I apologize for, I also apologize in advance for any reference I might have missed. Basically, this is just a huge disclaimer plus an invitation for you to just ask me questions, interact and everything as much as possible. All right, so just to give you a quick overview of what I'm going to do, what I want to do is I want to try with this talk to spur some discussions, right? Discussions in good faith, meaning it's not meant as a critique in a bad way or anything like that. The main goal is really to find common ground, right? Common ground is the importance of common ground is perhaps the biggest lesson that came from the 2024 Nordita workshop for those who were there. Basically, we learned that a bunch of people working in different quantum gravity communities sometimes don't even agree on what the questions are, let alone the answers. And as such, the first step in my talk is going to try to find some common ground here. And how am I going to do this? Well, I'm going to try to simplify everything as much as possible and only tell you basically one thing. There's only one claim I want to make here. I seem to, my video seemed to have stopped here. So the main claim that I want to make is that in the sense that I will define it, asymptotically safe quantum gravity has no black hole microstates. This is what I want to say in the talk. But of course, the way I'm going to say it is through some, several lines of argumentation that may or may not be, subject to loopholes that I could not anticipate and so on. So to begin, I will start by some common ground, as I said. Now, how am I going to do this? Well, as I anticipated already, I want to stay on the realm of physical and conceptual arguments. I don't want to go through like specific approximation schemes or computational frameworks, because those are subject to technical subtleties, right? Things that can go wrong here and there in several ways. I am also happy to talk about those if there's time, but I'm going to prioritize, let's say, physical motivations. And even more so, I want to prioritize physical principles, right? So I will not talk about phenomenology here. I will not talk about like the standard model or cosmology or anything that has to do with how realistic the scenario is. I'm going to talk about how consistent the scenario is with physical principles, right? Unitarity, causality, and the like. And I really want to take the best approach that I can here, the most intellectually honest approach, which is to learn from this debate that has been going on for a long time, and try to revisit everything that has been said in light of the new language, new understanding that we have of theoretical physics, and really try to look for everything that can go wrong and address it and refine all the arguments, right? So this, in some sense, is what I would call the swampland approach done right, as opposed to the swampland approach done wrong, which is just to declare, this is inconsistent because it violates this thing that some people have said should hold, right? I want to support my statements with physical motivations, not with, this is a insert technical jargon, this is something that someone said, therefore this follows. No, I don't want to do that, right? All right, so any questions about the general outline of the talk? So, all right, so far so good. All right, so I will start with giving some common grounds, as I said, or at least attempts to common grounds. You're free to object to my definitions, but I want to at least lie down some foundations that everybody can agree on, at least on a conventional level. So I want to start with just a definition, right? What do I mean by asymptotically safe quantum gravity? So I want to be as precise as possible for the purposes of this talk, so that there's no ambiguity, or at least the minimal possible amount of ambiguity. And the definition I want to use is literally just a QFT of gravity, the quantum field theory of gravity, right? But what does this mean? Concretely, well, the gravity part is easy, right? It just means that whatever this is ought to reduce to gravitational effective field theory, which is the standard of low energy physics that we all employ, right? And by gravitational EFT, I really mean something that is dominated by general relativity, right? By Einstein gravity, plus corrections. And I want this physics to take place in more than 3 dimensions. This is because, well, first of all, in below 4 dimensions, gravitational physics simplifies way too much. There are no gravitons and so on. And essentially everything that I'm going to say fails. Also, the GR part is because, changing the long distance structure of gravitational physics is very dangerous, right? Like it can incur in all sorts of inconsistencies, violations of causality, let alone, of course, non-realistic models. But as I said, this is beside the point. So I really want some local gravitational effective field theory here. As for what I mean by QFT, I just literally mean QFT in as standard a sense as you can imagine, which means that it has to be a UV complete relativistic theory, quantum theory of fields, right? UV complete is the key, because otherwise we're just doing effective field theory, right? So that we're not learning about quote unquote true quantum gravity, right? So the UV completeness is really important here. And this means effectively everything that asymptotically safe gravity is based on, the existence of an ultraviolet fixed point, right? Which everybody is very familiar with here. So the existence of the ultraviolet fixed point is essentially the part that makes asymptotic safety what it is, by definition. Everything else is just standard quantum gravity, namely, I want my quantum mechanics to be standard quantum mechanics. I want unitarity to hold. I want causality to hold. I want there to be stable ground states in Hilbert space. Everything that any quantum mechanical theory has, right? Regardless of gravity. So effectively, this means that all I'm adding to the definition of quantum gravity that I would use here is just the fields part. I want this quantum theory of gravity to have fields, which means that the UV completeness comes from an ultraviolet fixed point, right? That's what it has to be. And of course, being a field theory, there are other characteristics that will come into place. By the way, if you still can hear me because of this weird setup, if something goes wrong, please let me know, because I'm not very much in control of what's going on here. In particular, my phone battery is draining, and I'm a bit scared. Anyway, I will keep going, and I saw Aaron give me the thumbs up. I hope everything will be fine. All right, so this is the definition. How do we go further from here? Well, I want to say some stuff that should be true for any quantum gravity theory, right? And in particular, something about the scales and the couplings of quantum gravity and what they mean. So first of all, this picture, displays the 2 points in the space of energy scales that are certainly relevant for gravity, namely the absolute minimum and the Planck scale, right? The Planck scale is certainly a very significant energy scale in gravity. And when we start our investigation of an ultraviolet completion with some low energy EFT, right? This EFT is going to have a cutoff, right? By definition, again, I'm not saying anything controversial. What is the case also, beyond having a cutoff, is the following dichotomy. So above this cutoff, my EFT may either give way to full-blown UV complete quantum gravity, whatever that is, or give way to another EFT, right? There just may be another EFT that takes its place. This can happen also in a higher number of dimensions. Like the starting effective theory may, decompactify, so to speak, once you reach some energy scale that sees the size of some extra dimensions that were there but you couldn't see before, right? So without loss of generality, we can just ignore this issue of extra dimensions, because extra dimensions are a field theory kind of thing, right? They don't require UV completion to talk about. So without loss of generality, I will assume that there are no extra dimensions. If there are, just decompactify all of them and go to the maximal possible dimension of your theory, whatever that may be, 4, 17, whatever. So the dichotomy is either there is another EFT above my cutoff, or there is full-blown UV complete quantum gravity, whatever that is, right? And if there is an EFT above my cutoff, there will be another cutoff for my new EFT, right? And then the dichotomy presents itself once more. So the idea is that I can just repeat this process until I exhaust all my EFT descriptions, all the possible EFT descriptions that are available for my, let's say, low energy phase that I started from. At some point, therefore, I will reach this quantum gravity cutoff. I'm denoting it by lambda QG here. And above lambda QG, again, by definition, the full UV completion must kick in. Now, this is a scale that sometimes in the literature has been called the species scale. I will not need this term nor its meaning in this talk, but again, feel free to ask me about it or write to me in the future. So this is, again, this is just a definition. Now, what happens here? Well, in order to characterize what happens, I can define a gravitational coupling, right, by this ratio here, raised to some power for convenience. This is, again, just a definition of what I mean by gravitational coupling. The reason why this is a sensible definition is that the low energy EFT assigns a coupling strength to gravitons that scales like energy over Planck mass to the power d-2, right? So this is basically what the EFT would tell us that the coupling between gravitons is at the quantum gravity cutoff, right? Furthermore, this coupling is also related to the entropy of the smallest possible black holes that are described by EFT, right? It's essentially 1/s. This gives us the opportunity to define what weakly coupled quantum gravity would be, not just generic quantum gravity, but a weakly coupled UV completion, right? So here, by weakly coupled, I mean arbitrarily weakly coupled. I mean that the coupling strength can be made to be arbitrarily small, right? So this is not in contradiction with some other claims that I've heard in the asymptotic safety literature about such a scenario being weakly coupled in a numerical sense. Maybe this G is 0.1 or something. This is not what I'm talking about. I'm talking about arbitrarily small, right? This is important because it can be shown that when G can be made arbitrarily small, the UV completion must enter via tree-level effects. It cannot happen through loops or non-perturbative effects, right? This was shown by a simple H-bar counting argument by Cheng and Remeng 10 years ago now. And the consequence is that we cannot just have finitely many types of fields that UV complete the theory. Like, this does not solve the UV issues of gravity at tree level, right? In particular, this means that we need infinitely many types of fields, and these infinitely many types of fields have to take the form of a higher spin tower, which is what happens in string theory. And this can be further reinforced by a lot of works here that imposed constraints from unitarity and causality on gravitational amplitudes at tree level once again. The upshot is that a tree-level UV completion of gravity takes the form of something stringy, so to speak, like something very far away from a field theory. And the consequence is, let's say the first claim that I'm making that I hope is common ground that we can all agree on, is that asymptotically safe gravity cannot be weakly coupled in this sense, arbitrarily. Right? In other words, parametrically speaking, the quantum gravity cutoff is just the Planck scale, right? And this is where strong coupling effects, let's say non-perturbative physics, must enter, right? Which is in fact exactly what everybody has been saying for a long time. I'm just saying this is factual as far as we can tell. All right, so now we can actually get to the juicy part of the talk, where discussions can be less agreeable, perhaps. Yeah, I really hope that my battery will hold until the end of the talk. All right, so any questions about the common grounds that I laid out until now? So this is hopefully stuff that everybody can agree on, let's say. I'm not hearing any questions, so I will proceed. All right, so as I said, the main claim that I want to make is that asymptotically safe gravity has no black hole microstates, right? Black hole microstates meaning whatever degrees of freedom accounts for the Bekenstein-Hawking entropy of large black holes, right? Which is something that can be accessed semi-classically, right? Within the regime of validity of the EFT. So the three main arguments that I want to provide are these three. So they're based on considerations of density of states of black holes, gravitational amplitudes that involve black holes, and topology fluctuations of space-time. So the first is essentially the fact that the density of states of black holes as a function of energy grows way too fast to be accounted for by field theory degrees of freedom, right? Of course, if you go to the black hole background and you look at the entropy of, the macroscopic entropy, you see the area law, but this is a macroscopic entropy, not a microscopic counting, right? Which should be accounted for by field theory degrees of freedom in this kind of scenario. The second line of argumentation is based on amplitudes through the fact that black hole microstates, if they are present, should dominate the exchanges, right? So even if I scatter, I don't know, two particles into two particles, intermediate states will be dominated by black holes because of the above density of states growth, right? And then this actually, let's say, at least with some assumptions, this implies that the amplitudes go down super exponentially fast, which is in violation of the scale invariance of an interacting UB-complete Q of t, right? And finally, the most kind of sophisticated, mathematically sophisticated, perhaps, line of argumentation has to do with the topology change of space-time. And this is connected to black hole microstates because the semi-classical EFT calculations that produce the macroscopic, counting for black hole entropy all have to do with topology change in one way or another. So let's start with the density of states. Now, as anticipated, you just take the Bekenstein-Hawking area law and you substitute energy instead of size, and you get density of states that scales faster than exponential in the energy, right? Now, the claim that this cannot come from field degree of freedom arises from the fact that fields are local entities. Now, I'm not saying that the dynamics is local, right? This was a point made in some preceding discussions, that if the theory is non-local or just not conformal, perhaps in the ultraviolet, maybe you can avoid the issues with the area law versus the volume law. Here I'm saying something very different. I'm saying that the scaling with the energy, not the area, is too fast. In particular, local objects, local fields, let's say the density of states that come from field degree of freedom, field degrees of freedom, arises from the distributional properties of operator valued fields, right? The standard, let's say, Whiteman kind of framework where you take correlators and you express correlation functions in terms of them. And there are limits to how fast these kernels, these densities of states can scale, right? Which were worked out by Jaffe long ago. And, the exponential scaling is kind of the limit, specifically because the canonical partition functions that come from these field degree of freedom will diverge at any temperature, right? At any finite temperature, the integral over energies, including this density of states, will diverge hopelessly. This is sort of a hint that some non-field theoretic degrees of freedom must enter the picture, right? So as I anticipated before, this is sort of a refinement of the arguments that were discussed long ago in these papers that I'm citing, and many more. Now, are there any questions about the density of states?
In fact, we had a bit of discussion, or very bit of discussion, about the question whether there's a perturbativity assumption in this formula.
Very good, very good. So this formula holds for large black holes, is the idea. Right? So the idea is large black holes are perturbative. Let's say or rather the curvature is typical curvature scales are small, and the EFT description seems to be reliable. And this is kind of a weird situation in which the ultraviolet physics mixes with the infrared physics, because we are saying that the very high energy spectrum is actually dominated by very low energy objects, right? So this is the idea. Now, the way that this can fail is if the theory has no black hole microstates, right? So this is why I'm making this claim that asymptotically safe gravity has no black hole microstates, because it seems to me that that's the only way to account for this. In other words, this formula is wrong, right? When there are no black hole microstates. Does that answer the question? Now I'm much more relaxed and I can actually, take my time and answer questions and so on. So please, by all means, feel free to ask.
The original question was by Elijah, I think. I don't know if it answered that.
Yeah, that answers it. I think so when you say no black hole microstates in this context, do you just mean like no singularity? Or I mean, there's objects that have event horizons, but yeah, so what do you mean exactly by a black hole microstate?
So the idea is that the EFT tells us that there is a macrostate which is described by a geometry with a horizon. The singularity part is probably just fake, it's beyond the regime of validity of the EFT, we can scratch it, but the horizon is very much real. And the presence of a horizon gives us this macroscopic entropy. So what I mean by black hole microstate is a pure state, right? Or let's say, I mean an ensemble of pure states in the quantum gravitational theory, such that a micro or microcanonical or canonical or grand canonical ensemble thereof, depending on what kind of black hole you're looking at, reproduces the thermodynamical properties of the black hole macrostate that the EFT describes. That's what I mean by black hole microstate. So it has to be a pure quantum state, and of which I can build an ensemble. And the claim here is precisely that such pure states are not field-theoretic in nature. They do not arise from a bunch of field excitations, no matter how strongly coupled, no matter how non-local their dynamics is. This is what I'm saying.
Thank you.
Yeah, thanks a lot. All right, now that everything is more relaxed, I think I can keep going without rushing. All right. So this is the first argument using the density of states. Now the second argument goes further, right? It uses this fact. Now, again, the spirit of this work is really to question all the little bits and pieces of all the arguments that people have tried in the past, both to criticize and to defend, asymptotically safe gravity versus any other physical thing that can happen, the absence of black hole microstates or the absence of conformality or any other thing. Here, what I'm trying to improve upon preceding discussions is the fact that, at least the claim is, that we don't need black holes to be produced by gravitational scattering, right? In order to make this argument. So I just need there to be black hole microstates at all, and I need them to enter in the gravitational amplitudes as a completeness relation, right? Which is just what follows from unitarity. So all I need really is that gravitons or any other, let's say, some particles degree of freedom couple to black hole microstates if they are there. This is all I need. When this happens, you can resolve any scattering amplitude here. Let's say a 2 to 2 scattering amplitude, the matrix element of the S matrix, into a completeness relation, right? This completeness relation will include all the states in the Hilbert space, in particular black hole microstates. And the point is that if black hole microstates are present, at large center of mass energy fixed angle kind of processes, their density of states is so much bigger than everything else in the Hilbert space, let's say in the Hilbert space at fixed center of mass energy, that they will dominate the completeness relation. So the idea is that I can approximate, as you can see here, I can approximate the sum over intermediate states, here labeled by A, with black hole microstates, and I get, let's say, 1 by unitarity. This means that I can solve for matrix elements of my, let's say, initial state, particle state, into a black hole microstate in terms of the entropy, right? And some phases. Now, these phases were argued to be random, or let's say pseudo-random, of course, in these series of papers. And this is, at the very least, I think, a reasonable assumption that, of course, is subject to question, and then future works may or may not prove it or disprove it, but at least in other non-field theory examples that we have, it seems to work. And what happens with this kind of structure for the coupling between initial or final particle states and black hole microstates is therefore that by using the optical theorem we get this sort of super exponential decay for a 2 to 2 amplitude. So what happens is that the intermediate states here get dominated by black hole microstates, and then we can use the results from before, from unitarity. Well, everything here uses unitarity, really, to conclude that the imaginary part of the amplitude, which is also connected to the real part through the optical theorem, is super exponentially small at large center of mass energy, right? By using this sort of statistics of pseudo-random phases. Of course, the real amplitude will have sort of an envelope that decays like this, and then there will be wobbles around it. And these wobbles have been studied in certain toy models or low dimensional gravity, and but the envelope seems to be stable like this. And this is why I claim that these amplitudes are in sharp contrast with the idea of an interacting ultraviolet fixed point, because an interacting ultraviolet fixed point will give us sort of, well, scale-free amplitudes, right? That scale with the appropriate power of S. So this is argument number 2. So any questions about this? So let's say, as a summary, I've argued that both the kinematics and the dynamics of black hole microstates are incompatible with UV complete field theory description. Which is not to say that the field theory description is necessarily inconsistent. I'm just saying that there is a contradiction between the two of them. So either you throw one out or you throw the other out. And then, the fun part begins. The fun part is, can we make this theory work without black hole microstates? What do we have to change, or what do we have to explain? And this is where the fun begins. This is why I'm trying to frame this talk in a constructive way, in a way that everybody can learn something about physics, us included, of course. So there seems to be no questions about this.
Actually, I had another very basic question.
Yeah.
So presumably if it's a CFT in the UV, then there's no S matrix, right? So would this argument not apply there, or?
Well, if the theory were a CFT throughout, like full bona fide conformal field theory, then yes, the S matrix will be, let's say, infrared problematic, if I can use a diplomatic term, yes. But gravity is not, even if the ultraviolet fixed point were controlled by a conformal field theory, the actual physics is not conformal invariant, right? It's only asymptotically such at high energies. Yeah. There are potentially other issues with infrared S matrices, but let's say they can be sidestepped in several ways. One of which is to just scatter massive particles, which seem to exist in our universe, for example. All right, but thanks for the question. Okay, so now these two arguments were sort of self-contained. One is about the kinematics of black hole microstates, and the other is about the dynamics of black hole microstates using unitarity and the validity of the EFT. Now I will talk about the third line of argumentation that uses topology change, and this is going to be perhaps more, let's say, alien to part of the audience. So I'm very much available and with full battery now to discuss all of that. So what do I mean by topology change, and why is it relevant? Well, by topology change here, I mean that a gravitational theory ought to include a sum over space-time manifolds, space-time topologies. So not just metric tensors on a manifold or whatever local gravitational degrees of freedom, tetrads, field binds, spin connections, and what have you. That's local data. Topology change means that whatever makes the path integral of your theory, if it's a path integral or something else, whatever that is, ought to sum over global gravitational degrees of freedom, the space-time manifold itself, right? Now, this is in a very natural analogy with all the other physics theories that we have, right? In particular here, my first point in the slide is that it's a natural analogy with Yang-Mills theory, where in fact we are forced to sum over global degrees of freedom of gauge fields, which are principal bundles over the space-time manifold. And of course, this is a strong form of what we call background independence, right? So we want our physics to be independent of as much as possible about background data. In particular, in this case, it will be independent of everything except boundary conditions at infinity, right? So the idea is that even if we sum over space-time manifolds in some even just semi-classical approximation of a path integral, the boundary data at infinity will not be summed over, because any fluctuations of boundary data is infinitely suppressed by infinite actions worth of action. And this leads to the statement that usually, everything you need to specify about quantum gravity is boundary data at infinity. Everything else is summed over, right? In particular, states live at infinity. Observables are defined by boundary data only, and so on, right? This is why we use the S matrix instead of local correlators, for example. There is no such thing as local correlators if we sum over topologies. So another reason to sum over topologies, and this is why this thing is relevant for what I want to say about black holes, is that by summing over topologies, at least in a semi-classical way, which means summing over saddle points of the gravitational action, which is a finite set of manifolds, we reproduce black hole thermodynamics. So the idea here is that the original calculation by Hawking using this the Bogoliubov method and quantum fields on the black hole background, that is sort of an indirect calculation of black hole thermodynamics, because it says that quantum fields are in equilibrium, in approximate thermal equilibrium with something, and that something is supposed to be the degrees of freedom of the black hole, right? So that calculation is indirect. The gravitational path integral provides us with a direct derivation of black hole thermodynamics, because it calculates it straight from the gravitational degrees of freedom. That's the idea. However, in a macroscopic way, not a microscopic way. And there are at least two ways that the gravitational path integral can produce black hole entropy, for example, both of which use summing over topologies, right? So either the traditional Gibbons-Hawking, grand canonical partition function of gravity that uses the gravitational path integral with thermal boundary conditions, that is a sum over saddles that includes manifolds with different topology. And more recently, there is another calculation that uses, let's say, the von Neumann version of the entropy rather than the thermodynamical version of the entropy, where you compute like a trace of a density matrix by calculating the overlaps between semi-classical quantum states. And these overlaps are path integrals that involve sum over topologies again. And in both cases, the answer that the calculation spits out is the Bekenstein-Hawking area law plus subleading corrections. Okay? So and another way that summing over topologies explains the area law, like physically, is that by summing over topologies, again, the only physics left lives at the boundary. And let's say a natural way to explain the area law in the interior space-time is that the physics at the boundary be local. So an extensive law on the boundary translates into an area law in the interior spacetime. Right? This is a holographic version of this Einstein-Rosen equals Einstein-Podolsky-Rosen kind of correspondence between quantum entanglement of states on the boundary and topology fluctuations of the interior spacetime. So the point is there are several motivations to some of our topologies in quantum gravity in general, but I am going to claim eventually that in asymptotically safe gravity this cannot work. Now, what are some consequences of topology change? So in other words, why can't I just not do it, right? The reason is that if I don't, again, the holographic physics on the boundary gets destroyed, right? One way to explain this is that if the physics on the boundary is local, which is what we want to explain the area law, at least for, again, for large black holes, the locality of boundary physics tells us that, let's say, entangled quantum states of gravity defined as this boundary theory, because again, summing over topology gets rid of the interior. Entangled quantum states on the boundary should describe space-time manifolds in the interior with different topologies. And because, the Hilbert space is just spanned by all these possible states and I can just entangle them freely, all of them, I can entangle them, I can disentangle them, and so on, by considering different regions of the boundary and considering pure states that are, either tensor products or entangled superpositions thereof. All the topologies that are described by these quantum states in the semi-classical limit should be included in the sum, right? So if I don't include them, something goes wrong. And in some sense, the fact that summing over topologies should be encoded in the boundary by quantum entanglement of localized states on the boundary tells us that somehow the sum over topologies should be redundant, in the sense that summing over topologies is just doing the trace over the Hilbert space, but then we trace too much. We include the tensor products of states, and then we include the superpositions of tensor products of states, entangled superpositions, as if they were inequivalent. But really they are the same. They are just part of the same, they are spanned by the same orthonormal basis of the Hilbert space. So these people in these papers have studied this idea that the sum over topologies is there, but is redundant in the sense that we should be able to remove it somehow, right? We should be able to organize the sum over topologies in some classes, and these are classes of cobordism, if you're familiar with this term, but we will not need it in the following. And all these classes should basically give you the same contribution. So ultimately, we are summing over the same thing over and over, right? Now, did I just say that we do not need to sum over topologies? I did, but there is a price to pay, right? The price to pay is that there should be degrees of freedom in this gravitational path integral that replace the effect of summing over topologies, right? Because, as I said before, summing over topologies in the semi-classical limit has a purpose. The purpose is to reproduce black hole thermodynamics. So if you remove the sum over topologies in the semi-classical limit, something has to replace it. And this is UV physics, new UV degrees of freedom, that I just argued cannot be field-theoretic, right? So to be even more detailed, the reason why I am claiming that these UV degrees of freedom that replace summing over topologies cannot be field-theoretic is that there are sort of structural issues in summing over space-time manifolds in quantum field theory. One issue is sort of technical in the sense that how would you even do it, right? If there are no degrees of freedom that replace the sum over topologies, because you only have fields by definition, the only thing you can do is to actually sum over topologies. You cannot replace the sum with something else, right? As happens in a non-field-theoretic EV completion. In a field-theoretic EV completion, you need to sum over the actual manifolds, but there's no way to do it, right? There are uncountably many. There is no at least clear way to do it. And once we sum over space-time manifolds, assuming that we figure out how to do that, there is no way left to perform, like to define the theory in terms of RG flows or continuum limits with the physical cutoff, because there are no physical scales left, right? The physical length scales arise from the space-time geometry, dynamical or static as it is. But here we're summing over the topologies. So the only thing left is to use auxiliary RG scales, which is something that is routinely done. But if there is no physical counterpart to an auxiliary running scale, it's not obvious that what is being done is actually a bona fide RG flow, or at least that it mimics an RG flow. It could be something completely different, and then the physical meaning of it can be, jeopardized. Another reason is that, again, structurally, a QFT is something that takes a space-time manifold as an input and spits out, a bunch of observables and states. So it is, here I'm writing functorial, which is a categorical jargon to say that takes it as an input and changes accordingly as you change the input, right? So it's sort of space-time covariant rather than space-time invariant, which is what will happen if you sum over the manifolds, right? This is because the space of fields that you get changes as you change the space-time manifold. So there's no clear way of saying, this field instead of some other field when you change space-time manifolds. So if we therefore just let go of the idea that we should sum over topologies at all, because there is no sum over topologies, and there is no extra, set of degrees of freedom that is non-field theoretic and can replace the sum over topologies to account for black hole microstates, the conclusion is that simply there are no black hole microstates once again, right? And this leaves us with this question that the derivations of black hole entropy that are based on topology change are just gone. There is no topology change anymore. But there is this indirect derivation, the original one with the field fluctuations on the background that still needs some sort of explanation. Now, the explanation can simply be, it looks like an entropy, but it's not an entropy. It does not need microstates. But whatever the explanation is in asymptotically safe gravity, well, it should make sense, let's say. That this is what I'm saying. Whatever it is, it must be there.
Ivano?
Yes.
How many more slides do you have? Just because...
like a couple, like 2.
Can you try to sum up in the next 5 minutes?
Absolutely, yes.
Thanks.
No, because of course there was a delay with all the...
Sorry, Ivano, a question? Sorry, just real quick. This idea of no physical scales beyond the Planck mass. All this, is it just in pure gravity? And so you're saying I want black holes also in pure gravity? Or, because if I consider gravity with matter, then it is, I guess maybe I don't really know what you mean by auxiliary scales, but this is something that that was not clear to me. Sorry.
Right, very good. So what I meant was not the absence of any physical scale. What I meant was the absence of any running physical scale, right? Something that you can use to define an RG flow or a continuum limit by saying, the path integral is the limit of these cut-off things, right? So usually one takes the spectrum of a Laplacian operator or something on a fixed manifold. Of course, then the metric is dynamical, but it doesn't matter. At least it matters less than not having the manifold in the first place. Yeah, that's what I mean. So it's like using the lambda cutoff instead of the k cutoff, if you will. Yeah. So if you only have the k cutoff and you don't have the map to the physical lambda cutoff, then what are you really doing an RG flow? That would be the question. Yeah. Very good. Yeah, so this is basically the summary, really. I'm just saying that, I'm claiming that there are no black hole microstates, in addition to other structural features of the theory, namely, it's not weakly coupled in the sense that I said, who cares? And it's not holographic. Again, who cares? Insofar as there is an answer to the question, if no black hole microstates, why does it look like black hole microstates, right? Why microstates shaped, so to speak? So this is the end. I'm just going to state again that basically the assumptions were sort of really standard but strict, right? So I'm using standard quantum theory, standard EFT in a very strict way. Therefore, you can certainly avoid the claims that I made by just changing something here and there. So something about the foundations. Maybe you don't care about unitarity, for example. Maybe you don't care about causality. Maybe quantum mechanics is wrong, right? There are some people who investigate this scenario. So it is a free country, as I wrote here. You're free to do so, but this will not apply to my discussion. As for the actual claim, within the bounds of these assumptions, something else that can change, as I stated a couple of times, is long-distance modifications to the EFT. So it will not be a standard local EFT dominated by Einstein gravity, but rather something else. And this allows you to avoid essentially most, if not all, of swampland constraints, right? And this is why I focused on the motivations behind swampland constraints, because they all basically follow from black hole physics. So if black hole physics is just not there in the microscopic sense, then you can just ignore all of that, right? But there still needs to be an explanation of the origin of this difference. And finally, I wanted to mention basically something that can be done while ignoring all of this. So basically asking, can there be a UV completion of gravity within field theory without black hole microstates, right? And a way to do this concretely is using non-perturbative methods of the S-matrix bootstrap, because these methods give us bounds on certain pieces of scattering amplitudes that can be compared with, let's say, functional RG calculations, dynamical triangulations calculations, and what have you, that use the presence of an ultraviolet fixed point. So I am now done. Thank you very much. And again, I'm so sorry for all the technical complications.
Thank you very much, Ivano.